Welcome to a new episode of the ITU Journal webinar series, where you can find insights and forward-looking research on future and evolving technologies. The ITU Journal is an international journal providing complete coverage of all communications and networking paradigms, free of charge for both readers and authors. This publication considers yet to be published papers addressing fundamental and applied research, building bridges between disciplines, connecting theory with application, and stimulating international dialogue. Its interdisciplinary approach reflects ITU's comprehensive field of interest and explores the convergence of ICT with other disciplines. We count on your support to make this webinar an interesting experience. Please submit your questions via the Q&A channel at the bottom of your screen. All questions from the audience will be taken during the Q&A session after the talk. The meeting is being recorded and the recording will be made available on the webinar website. Closed captioning is also available for this event. You can enable this by clicking on the closed caption icon at the bottom of your screen. We hope that you will enjoy the talk and we encourage you to stay connected until the end for the Wisdom Corner. I will now give the floor to our Master of Ceremonies.
Hello, and welcome to the webinar series with academics of the ITU Journal on Future and Evolving Technologies. My name is Alessia Magliarditi from ITU, the International Telecommunication Union, the United Nations Specialized Agency for Information and Communication Technologies. It is my pleasure to open our webinar today with Professor Albert Somaya from the University of Sydney from Australia. We count on your support to make this webinar an interesting experience, so please submit your questions via the Q&A channel. We will address them to our speaker during the Q&A session. After the Q&A, as just announced by our avatar, I will moderate the Wisdom Corner, live lessons, so please stay online. Professor Somaya agreed to a personal chat. He will share with us some lessons learned over the years that might perhaps be useful for some of you. I'm pleased to introduce now the moderator of this webinar, Professor Ian Akilditz, Editor-in-Chief of the ITU Journal and founder and president of TRUVA from the United States. Professor Akilditz is Ken Byers Chair Professor in Telecommunications Emeritus at the Georgia Institute of Technology. He has established many research centers worldwide, including in South Africa, Spain, Saudi Arabia, and Finland. He's Editor-in-Chief Emeritus of Impact Factor journals, highly cited and at the top of the most prestigious international ranking, visiting distinguished professors in several universities around the world. His current research interests include 6G wireless systems, terahertz communication, metaverse, and communication in challenged environments. So, Professor Akilditz, the floor is yours to introduce our speaker and to moderate the Q&A session. Thank you.
Thank you, Alessia. Also, thanks to both Marias, as well as our speaker today, Albert Somaya. Greetings from Istanbul to all around the world. I welcome you all to our ITU Journal for Future and Evolving Technologies webinar series again. We have another excellent speaker today, Professor Albert Somaya from University of Sydney, Australia. We greatly appreciate Albert's sacrifice to join us as it is almost midnight in Sydney. Before I present Albert in detail, I would like to briefly talk about our journal. The objective of our journal is to bring the academic and industrial worlds together in order to establish a strong bridge between academia and industry. The idea for our journal was initiated back in December 2019, and our first issue was published in December 2020. It is an open access journal, no fees for readers, no fees for authors. The papers go through a rigorous review process, and we try to cover all forefront and timely research activities in the academic and industrial world. The journal is a product of a big team effort, and I would like to acknowledge them here. Sizo Ono-san, Bilal Jamusi, Alessia Magliarditi, and Erika Campilongo, and both Marias today, and many others for their work, efforts, continuous support, and dedication for the success of our journal. I encourage you all to submit your papers, and also if you have ideas for special issues on popular topics, please do not hesitate to contact us. Today, I have the great pleasure to present you our speaker, Professor Albert Zamaya. First of all, on behalf of our entire journal team, I personally thank Albert for accepting our invitation and giving this webinar today. Albert is a Peter Nicol Russell Chair Professor of Computer Science and Director of the Center for Distributed and High Performance Computing at the University of Sydney. He has published over 800 scientific papers and articles, and is and co-author as well as editor of more than 30 books. A sought-after speaker, he has delivered over 300 keynote addresses, invited seminars, and media briefings. He is the past editor-in-chief of the IEEE Transactions on Computers, IEEE Transactions on Sustainable Computing, and the ACM Computing Surveys. Albert is a decorated scholar with numerous accolades, including IEEE Fellow, the American Association for the Advancement of Science, and Institution of Engineering and Technology. Also, he's a fellow of the Australian Academy of Science, Royal Society of New South Wales, a foreign member of Academia Europaea, and a member of the European Academy of Sciences and Arts. Some of his recent awards include the Research Innovation Award, the IEEE Technical Committee on Cloud Computing in 2021, the Technical Achievement and Recognition Award, the Communication Society's IoT, Ad hoc and Sensor Networks Technical Committee in 2022. Albert is a Clarivate 2022 and 2023 highly cited researcher, and his research interests lie in parallel and distributed computing, networking, and complex systems. Based on Google Scholar, Albert's H index is 87, and the total number of citations to his papers is 45,000 citations. Albert contributed many pioneering papers to our research field, in particular to the areas of big data, data centers, and cloud computing systems, federated learning systems and wireless networks, edge intelligence, and remote sensing and IoTs. He continues to produce high-class and impactful papers. Without further ado, let us listen to the exciting talk. Thanks a lot again, Albert. We look forward to listening to you.
Thank you, Ian. Very kind of, very kind invitation. I highly appreciate it, and also very thankful for your, kind of also very kind introduction. Thanks for Alicia for following up with all of the emails and setting up this presentation. And I hope, let me first share my slides, share the screen. Okay, can we all see this?
Yes, thank you.
Okay, very good. So over the next 15 minutes maybe, or just under an hour, I'll try to share with you some sort of lessons learned, right? I mean, we've been working in this field, like Professor Akil said, for the last few years. We've built up enough experience, observations, words of wisdom, if you will, in trying to understand, this whole new confluence or this new marriage of machine learning and mobile computing or distributed systems or even edge computing. So in the next few slides, I'll take you through a very short journey about some of these concepts that you normally get to hear every time you hear about machine learning and the edge, or even machine learning on its own, and then try to really connect these concepts, right? So at least trying to make sense why these concepts appear, why they are needed, is there any historical background for, how they emerged and so on. And then hopefully try to connect all these dots and give you some sort of a mini tutorial of this whole business of edge AI or using AI on the edge of the network. Okay, so right, let me see. Somehow it's refusing to move. Okay, maybe let me stop sharing and share again. My apologies, just bear with me. Okay. I'm gonna share again. Okay. Okay. Can we see this?
Yes, we can.
Okay, let me go back. All right. So like I said, some experiences, some lessons learned, and so on. So this is where we do most of this research. These are some of our partial funders, just a subset of those funders that we've been working on on these topics and others within the field of edge and edge computing, and of course the most recent, this marriage of edge and machine learning. So during this presentation, I'll take you through this brief, like I said, journey. So what is edge? What is generative AI? What are the main challenges? And then, give some snippets of solutions and approaches of how, we normally, or what are the issues that are important to when we're mounting, type of AI on the edge or moving AI to the edge, and what are the issues involved with optimizing and implementing these large language models, which I'll come and touch on as well briefly on in the presentation, and give some examples of some real world type of applications. Again, the edge, we've seen the edge, been talked about a lot in the last at least 15 years. And probably even if we trace the background of edge computing, we can see actually it goes back even to the 1990s. But again, it was called differently at the time. And then as we moved closer to the cloud revolution that took place, a few years back again, we've seen the push for moving again the power of the cloud closer to the end user, or where the edges, where data is being generated or data is being consumed by users. And the idea is just to move this power of the cloud closer to the user, where users don't really have access direct to clouds and so on. So I don't need to give you a long tutorial on the edge. It's a paradigm that again evolved over the last probably 15 plus years. And the idea of it is to bridge the response time and allow better use of bandwidth for applications that are close to the user. As you can see from this descriptive figure, you can see the edge, where the network edge sits at the extremities of the network where the user is sitting, and then of course all the way you go to the cloud core, or where the internet core is, where you have lots of data centers or virtualized type of data centers. And of course, as you move closer to the cloud, you get benefits. As you get closer to the edge, you get other benefits and so on. So you can see it's a balancing act between the two different types of technologies. But again, like I said, it's the idea, or the basic principles is proximity, is you're moving again data or moving computation, storage, even intelligence closer where the data is sitting, as well as we're decentralizing the computation. So instead of having everything being sent back to the cloud, we're moving the stuff closer to the end users. That could vary. They could be patients in hospitals. They could be people sitting in coffee shops. They could be people sitting in factories and the like, and so on. So different needs, different requirements, and so on. And of course, allowing real-time processing capability, because again, when you get closer to the user, you can really endow the user with with more power, with more needed type of resources. Again, the edge devices do vary. So when we're talking about the edge, you could end up with sensors, cameras, mobile devices, as many people working in the field of edge computing, or even people who work in networking know. And then we talk about some sort of more powerful devices like edge gateways and so on. And these are like intermediate devices that sit in the edge layer, because again, the edge could have multiple layers, so it doesn't have to be a single layer of the edge. It could be multiple layers, and these multiple layers do different or play different functionalities or different roles. And therefore, edge gateways could be really kind of an intermediate device that helps with aggregating data and getting things, kind of getting, if you will, the data connected in such a way that makes sense. And of course, we go to even a more powerful type of device, which is in this case the edge server. And in this case, this is again, providing the local edge with more or much needed, computational type of capability or resources to allow more complex data analysis or more like machine learning type of number crunching. Of course, the realm of edge computing is massive. I mean, we could sit here and for the next kind of a few hours and just talk about applications of the edge or where edge is being used. But of course, we've seen edge being deployed in autonomous vehicles. We've seen that in smart cities, industrial IoT, manufacturing, and the like, as well as like health is a big beneficiary of edge devices and edge computing. However, also like we talk about things like entertainment, multimedia, like games, movies being streamed, and so on. But most importantly, we've seen edge excel or also needed and also excel in what we call mission critical applications, where you have an application that cannot really tolerate latency, it cannot tolerate failure, and so on. So having an application which is running far away from the cloud will create all sorts of issues and constraints. And therefore, when you bring the computation closer to the edge, you're able to serve these type of applications that tend to be mission critical. Think of hardware sitting in the intensive care unit in a hospital, or sitting in a manufacturing facility, or sitting in a mining type of environment. Here, you cannot really tolerate failures. Otherwise, these failures could lead to catastrophes. And therefore, the edge becomes really kind of not a luxury, but more of a necessity that you need to really kind of deploy important type of kind of action closer to the user. Okay, so Gen AI or generative AI or Gen AI for short, we've seen again more talk about this this new old, I guess it depends on how you see it. It's a subset of AI which is again focused on creating data. So you have a set of data, old or existing, and you basically need something or an entity that could generate similar data to that that can be used in a variety of applications. We've seen things like GANs and VAEs and so on, and I'll mention those and talk about those shortly, that are being used quite a lot in the literature, and people do use them with edge and without edge. But of course, in the edge, they bring their own problems or their own constraints and so on. So the basic principles, you're trying to learn from data. So that's why you have training models on large data sets, trying to understand patterns and structures. And this has been the mission of AI or machine learning for a long time. Okay, we're talking about back in the 1960s, 70s, 80s, and so on. And of course, with that, you're trying to generate new content and based on learned patterns. So a neural network, for example, learns patterns based on existing data, and then hopefully it can basically generate new content based on what it learned, and so on. And of course, examples of such generated content, many of us have been exposed to much of that in recent times. things like, GPT-4, which is generative pre-trained transformer 4. Again, generating, type of, text, which is again coherent, hopefully contextually relevant. You ask questions and you get answers back and so on. Or, for example, even things a little bit more sophisticated, like image generation and so on, or movie generations and so on. And most in recent times, of course, more creative pursuits like, arts and music generation and so on, that can be used or can be, these systems can generate as they become more sophisticated. Of course, the idea is trying to generate content, and you're trying to automate that process, which is not easy. And that the content here again varies. So I don't want to really specifically say it's purely text, but it could be anything. Data augmentation, again, this is important for many applications, especially, for example, in health, when you're trying to train a system on existing data, but then the existing data, you need to use that to really build better insight into the system, like you're saying, to do some diagnosis and so on. Here again, you need to create synthetic data, which is as close as possible to the real data or the data that already existed. Like I said, healthcare is a great beneficiary of this type of synthetic medical data for research or even creating personalized type of medicines and so on and plans. And we've seen this being used in the recent times quite a lot. Of course, design and creativity is another arena, which I just mentioned a few seconds ago. Okay. Okay. Another thing that you've heard, I'm sure many of you have heard in this business, is what so-called LLMs, or large language models. And these again, models like GPT-4, for example, or ChatGPT. And this is like, like we said, so it's 3D text that can understand and generate human. So the system understands your questions and then try to give you a human-like, as much as human-like, type of text. And the applications are many. I'm just here, giving some sort of an example or a sample: text completion, translation, summarization, and then conversations and so on. Also, we hear the term generative adversarial networks, or GANs for short. And these are two neural networks, a generator and a discriminator. So basically, trained and a discriminator. So we have a generator which basically generate type of data. That discriminator kind of detects whether there is fakeness or not, whether this data is genuine or not, and so on. And the applications are again many examples: image generation, video synthesis, films, and so on, and data augmentation. And of course, VAEs, variational autoencoders, again, they learn to encode input data to latent space and then decode it back to the original space. Again, image reconstruction, anomaly detection, and generative design. And many of these, whether you're doing LLMs, GANs, VAEs, and so on, could be used in combinations, right? So they are not really kind of standalone things. Or within a given application, you could have multiple of these modules and agents. Some of it could be sitting on the edge, for example. Some of it could be sitting on a cloud, which is sitting in the back, and so on. So it could be really kind of mixing and matching of these type of environments. Again, LLMs, they're a type of deep learning model. We know about deep learning. We've been hearing about deep learning now for a few years. And of course, you can see the importance of this. You're training it on vast amounts of data, which could be something not easy to do with edge computing, because again, of the lack of data and so on. Understanding and generate human-like language. And of course, by default, having to run a deep learning model on the edge creates its own challenges because they're compute intensive, where edge devices tend to be, kind of compute constrained and could be battery operated and the like. And again, of course, here, we're leveraging a variety of type of ML or machine learning type of, agents or architectures, like transformers and the like. And then basically, you're learning a certain pattern, and you're trying to really basically during training, and then during runtime, you're trying to really tune this model to basically, kind of resemble or give you an output which is closer what you're looking for. Of course, there are ways again and techniques that I'm going to touch on in the next few slides to show you how do we really do this, and maybe do this in such a way that gives us a little bit of more efficiency, compute efficiency, and even storage efficiency. Okay, so again, because of the nature of LLMs, how they evolved, they normally run on big cloud environments and the like, and therefore you could use them, or you train them using massive and huge data sets like books, websites, written content, our information as users that we normally put on the internet, for example, for all sorts of type of applications or services and so on. And there is this pre-training stage in which, again, where we training the model on this kind of a huge amount of data, and this could be, for example, text. You're trying to predict the next word sentence and so on, and then of course the model itself will, because of it, learn so much, it can start helping you with fixing the grammar and maybe even providing facts about the world. Like, for example, you could ask questions about, can you find me the best beaches in Sydney that, for example, that I can visit that are child friendly or whatever. So in this case, the model basically learned this information from somewhere, and then it will start spitting out information that to help you with your query. And then of course fine tuning happen, where kind of adapting this knowledge that was gained to specific applications. So for example, the training could have happened on huge data sets for wide range of applications, for example, in health. In this case, the moment you start personalizing it, for example, for a specific patient, for a specific, for example, disease or condition, then here the model needs to, again, the tuning happens where you basically tailoring it for a specific case. Okay, notable models, again, chat, GPT-3 and 4 and so on. So these are all developed, and we've seen many of us probably are using it already. Many researchers and research students and the like, and even people in industry and so on. There is the kind of now more move into using these type of tools. Things like like I said, GPT in its different versions. You have, BERT is another system that's being used. You have T5, which is text-to-text transformer. Again, converts all type of, natural language processing, NLP tasks into text format, allowing a single model to perform tasks like translation, summarization, question answering, and so on. And of course, if you just do a search on this on the net, you'll find it will return so many entries, and you can see so much information on this in this area, and many tools and the like. Again, GANs, very popular, and we've seen them, and I just touched on this, and I said to you, so it's a tool neural network where a generator and a discriminator, they're working together, which are also like, working together in this what's called adversarial competition. So one generates data, the other finds if this data is fake, or trying to really reduce the amount of fakeness in the data. So again, it's learning, it's learning from realistic data. And it learns to generate, one of the networks learns to generate the realistic data by trying to fool the discriminator network. So you can see this type of game that played by two networks, excuse me, that allows us to really kind of hopefully get to a situation in which we have synthetic data, which is as close as possible to the real data. Okay, I think I've said this already. Applications are many. Again, image generation, video generation, again, text to image analysis, data augmentation, music and audio generation. You can see, so you can see where, for example, that can be used to generate a new, piece of music, right? Generating a new score sheet and so on, or even, trained on a number of images, and you tell the network to give me an image to do X or Y, that could involve real characters, real people, but then you put them in a different scenario, and then you get a new image, which is called AI generated image, that could include real people, but in a different type of scenario. You can see the applications are many of this type of work. Okay, so okay, so now why? So you can see, I mean, much of that is really, you know, talking about AI or machine learning that's been evolving over the last 50, 60 years. Much of it, again, was tailored to run on supercomputers, on cloud environments, on bigger systems and the like, because you're dealing with situations in which you're trying to really kind of number crunch a lot of data, and the size of these neural networks is just huge, and doing so, of course, that entails a lot of compute, a lot of memory, and so on. And of course, that creates challenges because we know that edge is important. The edge technology is here to stay. But now with ML or machine learning, it will add new value. It will add extra value to the edge. And of course, there are two ways of seeing this, right? So there are two schools of thought where they say, one, we're using the edge to run machine learning applications, or we're using the edge or we're using machine learning to manage the edge. So you can see the use of machine learning can be in multiple ways. However, you can also do the same. I mean, you can use the edge to run ML, while at the same time you could have ML managing the resources on your edge. So you can have ML at different layers in the edge environment. But of course, the challenges are like I said, the fact that you're trying to bring you know, type of environments that are normally running in big systems, trying to run them on low battery or low capability devices with very limited resources and the like, and that creates its own challenges. Okay. So computational limitations are one thing. Of course, there is limited processing power. We're talking about edge devices like we showed in the slide. They could be IoT sensors, smartphones, embedded systems, and so on. And for that, really kind of, you know, when you're talking about, you know, large, you know, kind of Gen AI models like you know, GPT-4 and the like, these requires massive compute resources. And for that to run these on an edge device is just, you know, kind of impossible because of the need of the compute needs and so on. So we also have not only the processing capability, but also we have memory constraints. Again, memory devices, edge devices have very little memory or very limited memory. And you cannot really load into these, you know, these massive or big, you know, kind of machine learning or AI models. So you need really, you know, efficient memory management, you know, model optimization techniques are very crucial for this. As you can see, I'm going to be touching on certain aspects of these challenges, and these in themselves could be really research areas, new research areas for people who are looking to really kind of work in this field. So you can see you need to work with limited processing power. You need to work with memory constraints. Also, there is the issue of power consumption, right? So we're running complex AI models that tend to run on clouds and the like. And then the moment you try, even if you're trying to bring, you know, light versions of these AI models or machine learning models, they still be, you know, consuming a lot of, if you don't know what you're doing, you'll still be consuming a lot of battery. So we need to do certain things or certain type of shortcuts to allow us to deal with this issue of power consumption. Again, if you run something which is really too compute intensive on edge device, which happens to be running on a battery, does not connected into the wall or to an electricity source, then that device will die out very quickly, and it will basically disconnect part of your edge environment, right? And if this is sitting, for example, in a smart home or like in a smart health type of environment, it could cause issues. And of course, running energy efficient algorithms. We've seen the need for these algorithms even without machine learning. So when you're trying to run an application or a service on the edge, you need to make sure that what you're running there could be, you know, could be running, or the code that you're running is energy efficient. So to deal with the issue of power consumption. And there are different techniques that people from the field of computer architecture know, and much of these techniques are now part and parcel of all the hardware that we normally use, even on day-to-day basis. Things like dynamic voltage scaling or dynamic frequency scaling. These are the different techniques in which are used to basically allow the system itself to really run for the longest period of time, without having to consume too much energy. And that's by putting certain part of the application, for example, into sleep when it's not being used, and then you bring it back into action when you need to use it, and so on. And there are, of course, a variety of techniques and algorithms by which you could manage this type of facility or capability. Data privacy is a big concern because, again, the moment you say, look, I'm going to put this data closer to the edge, of course, many of us say, for example, you're running health applications and you're monitoring your health from home. You feel a little bit at ease because you're saying, look, my data is sitting close to me. I don't need to really, share it with the rest of the world because I feel very sensitive about this data. However, of course, the moment you bring data closer to the user, you could open up other challenges. Of course, when you have the data sitting in the cloud, you'll feel a little bit more secure because, again, of the security protocols used within the clouds and so on. But the moment you move the data closer to the user, and different users are, you will use different, for example, security protocols. They could use different type of, they have different devices and the like. And of course, that makes security also a challenge, although the user will feel more safe because his or her data is sitting closer to them. But that could also create other issues because, again, not all users are experienced security experts, right? So it varies. Again, there are ways by which you could deal with this or work with this, and there are different type of encryption techniques and secure data handling, best practices and so on. Things like, again, federated learning. Many of us have heard about this term. It's been around for, again, a few years. And of course, differential privacy. These are all techniques used to and I'll touch a little bit on these in the next few slides. These are techniques used to help us feel a little bit more at ease with our data being used to do computation. Scalability issues, again, you're managing multiple devices. Again, the edge could have multiple depends. So at a home environment, for example, if your home is part of the edge, you could have maybe 10, 15 devices, right? So again, you could be adding more devices to your system. And of course, that could also create challenges. Scalability is also an issue in this case. And of course, deployment and maintenance. How do you really deploy and maintain these ML models on numerous edge devices, right? Because that itself, say, for example, your edge you could be a hospital, and your edge could be really all the patients that come and go to that hospital. So in this case, you have issues of scalability, you have issues of security, but you also have issues of how do you really deploy machine learning to help all of these patients, for example, because each of them will have different issues, different, for example, conditions and so on. How do you do that with deploying different AI models into these different machines or different edge devices? And while at the same time, you're trying to make sure that everything gets updated. We have monitoring, we have troubleshooting, and so on. So you can see the challenges that could arise from a situation like this. So solutions and approaches. In this case, again, there are techniques by which we borrow them, again, from traditional or classical machine learning and AI that have been used for a long time. Things like, for example, pruning, quantization, and these are all techniques used to really reduce the amount of computation by shrinking the size of the model. And the hope is that you're doing that smartly so that you don't really compromise the performance of this model. Again and again, you can again do a net search on this, look for things like TensorFlow Lite or PyTorch Mobile. These are all tools that offer us type of optimization capabilities for mobile and edge deployments. And of course, we get more of these tools as more interest arises in trying to deploy more machine learning on the edge. You'll find that there are more tools coming out on the market every day. Types of pruning: weight pruning, neuron pruning, layer pruning. If in a neural network, we know that a network will have an input layer, an output layer, and in between you would have neurons, and you would have each the neurons could be connected through weights, and of course the neurons could sit in different layers and so on. And techniques that deal with pruning weights and pruning layers and so on go back to the 1980s, in which you're trying to really again during that time I remember a time in which one of my early papers on neural networks actually dealt with this issue, and this goes back to the early 1990s. And of course, before that, there was even more work dealing with this issue of pruning and neuron pruning, layer pruning, and then weight pruning. And why this is the case? Because during the 80s, the 90s, compute, capabilities, were not, I mean, you cannot find compute capabilities all the time that can deal with the, with the computing needed to train many of these systems and so on. Of course, these days, the landscape, kind of shifted, and we have a variety of tools, techniques, and so on to be able to really kind of deal with compute models and architectures. However, still, when we talk about moving stuff closer to the edge, these issues of limited resources that were like big issues back in the day, kind of appear again, because again now we're talking about low power devices, talking about lower memory devices, low compute power devices, bandwidth is also an issue, and so on. And therefore, these issues will remain very active. How do you really prune a network, whether it's weight, layer, and neurons, without having to really lose accuracy or lose performance? So federated learning is one model by which we do that, in which we train or a model in which we do distributed training. So the model itself could be distributed across multiple devices. So a single device will not hold the whole model because it's a compute limited device, memory limited device. So the idea is that you distribute, the learning across multiple devices, and then and these models get trained on their own local data, because again, the data could be sitting, different data sitting with different type of users. And then, of course, each device basically uploads or downloads the current model, and then train on it, and then update the parameters back to the central server. So in a way, there is a central server holding the big model, and then, of course, the local devices will download this model, do their training, tuning, and so on, and then send the parameters back, to the local server. Think of it this way. Think of it like you have a large language model sitting in a big server, and then you download parts of it to a local edge device, where you do the local processing relevant to that environment for that local device, edge device, and then the parameters could be updated and sent back to the central model to update, and so on. So in this case, you can see, not all the model is needed, not all the data are needed at the local device. It will only use what it needs, and then deliver what it from the environment itself back to the local server, and sorry, the main server, central server. So here again, privacy and security is maintained, because again, the raw data does not leave the local device. So think of it again, you are having multiple patients holding their own local data, and then they do the training to improve the model for detecting certain, for example, condition like pain management, for example, for multiple patients. But each patient has a different type of condition that leads to pain that needs to be managed, and then the training happens locally, and then they send their parameters back to the local server, which is really basically running a bigger model to help with learning about pain management and deciding how to basically manage this, how to dispense, for example, painkillers and the like to manage this pain. So in this case, you're maintaining privacy and security of the data, because the local data never leaves the edge model or the local model. And of course, you can use techniques like we mentioned in the previous slide, things like differential privacy, or even like homomorphic encryption can be used to basically send the updates back to the central server. So even when information leaves the edge device to go to the central server, it can be encrypted. So at least if someone is intervening or interfering with this process, that they will not be able to really make sense of this data. Okay. Edge AI frameworks, they are, like we said in 2 slides ago, they vary again, but they're all like type of specialized libraries, software libraries, and tools designed to again facilitate how to really use and deploy machine learning models on edge devices. And we've seen, for example, in the literature, in the last few years, things like TensorFlow Lite, for example. Lite because it's lightweight for edge devices, and again it's compatible with Android, iOS, and embedded Linux platforms, for example, that can be used in a variety of real-time systems or even mission-critical type of applications, and supports quantization, pruning, and other optimization techniques like we talked about that are needed to make these models a little bit more efficient. And of course, Onyx runtime is another environment that can also help us with this and so on. And with capabilities to integrate with hardware accelerators like GPUs, like TPUs, tensor processing units, and even custom silicon that you're building type of for specific type of applications and so on. Okay, optimizing AI models for edge devices. This is really a big thing, and it's going to be big for a while with us, because as we see more value in putting these machine learning type of systems into the edge or environments, into these type of edge ecosystems, whether for health, for manufacturing, and for transport and so on. We'll see more of this type of need for optimizing these models kind of arises, and we need to deal with that. And of course, there are different ways, again, what we call lightweight model architectures. Again, lightweight because we're trying to take a model which is normally developed for a cloud environment. We're trying to make it lighter, and so that it consumes less power when it's running and consumes less memory again when it's running, and then that enables us to really deploy it on the edge. So again, there are different techniques and different, again, type of terminologies you would normally hear when we're talking about this type of process. So we're talking about things like efficient net. These are all new architectures. Again, the idea is you're trying to really perform a computation for the machine learning model and deliver a high level of accuracy, just like as if you're running the complete model or the more complex model. So in this case, you're running it with fewer parameters, with lower computational requirements, but then at the same time, you're not sacrificing accuracy, or you're not sacrificing the ability to really make the right decisions. Again, there are different ways by which to do this optimization for a variety of these type of environments. But again, like we said, there are lightweight type of model architectures, like again, efficient net, TinyML, and so on. Here again, it's very popular, especially with real-time applications. Again, because it's very suited for sensor data analysis, voice recognition, and simple anomaly detection, for example, in IoT devices and the like. So you can see the need, why we really need something which is lightweight, because most of your IoT devices are battery operated, and they all have very limited battery power, and they cannot really run for a long time. And therefore, we need to run these lightweight type of models. Mobile nets is another thing that uses depth-wise separable convolutions. Again, there are variants of this. I mean, like we could sit here and talk about this for the next hour. How do they do that, and so on. But it's this mobile nets is really ideal for mobile and edge application, because again, it knows how to deal with resource limited type of environments and so on. And again, I just like show briefly here what's the meaning of a normal convolution, and then we're talking about deep-wise and point-wise convolution. So you can see it's a mechanism by which we could really hopefully get more accuracy or better accuracy for our computation. And again, you can see it's an ideal way by which you could take an application that could run in the cloud and hopefully port it into an edge device. Okay. Model pruning, I mean, like I said, I mean, these are techniques that's been around for a long time, and the literature is full of these techniques. And the idea again is to help us reduce the model size and the computational load of these models by removing, again, less important weights or neurons or even whole layers from a neural network, and so on. And there are lots of techniques in the literature on how to do that, and even more techniques are getting invented, by the day, because again, it's an important part of really trying to come up with lightweight type of machine learning models. And of course, lightweight. And actually, these pruning techniques are not only important for lightweight devices, they're also important even for bigger systems. However, for lightweight devices, they are even more important. They become even more crucial. Quantization, again, here dealing with reducing the precision. However, again, there is a lot of work done in a topic called approximate computing, in which you're basically you're reducing the size of the bits that you're computing on, but at the same time you don't lose the accuracy, or you're trying not to sacrifice accuracy. In some cases, in many of these learning systems, you could deal with lower levels of accuracy when it comes to really doing predictions and so on. So you really don't have to have 99.99999% accuracy. You could really kind of say, look, I'm happy with a 70% accuracy or 80% accuracy in this case. And of course, quantization can be used again to significantly, again, reduce the model size and the computational required without impacting accuracy. Of course, accuracy is very important. And for many applications, what's known as accuracy could vary. For an application, you need, like I said, 99.99% accuracy. For other applications, could be, much lower. So it's a matter of a balancing act, right? Again, it's part of the optimization process. So you would use pruning, quantization, in kind of in a smart way, I guess, depending on the application you're trying to do that. Of course, other techniques come up, like things like sparse representations, where in this case you have networks where you have sparsity in the weights or the activations of the network, and this could be zero or near zero. So the idea is, how do you really deal with that? Again, you don't want to really be multiplying with zeros or even numbers close to zero all the time, which means compute time, which is being used not in a very effective way, and so on. And there are techniques by which you would deal with these big matrices that have a lot of zeros. And of course, that would help us reduce memory usage and computational load as well, because you're basically doing computation on only numbers that are non-zero numbers, or not even like near zero type of numbers. Of course, there are ways by which you would do this, because you don't want to also lose track of the computation. So there are techniques by which you would do this, but again, with that comes, of course, kind of ability to really kind of put smaller models into the memory, or even like do less or fewer computations on a given activity, for example, and that would be another technique by which we would use. Again, other techniques, again, for model optimization, if you do just like the search on this, you find like what we call low rank factorization, again, taking weights and decomposing products into lower rank matrices and so on. And that's all linear algebra type of techniques that we use to make so that you're computing on more more in a more effective way, right? And there are techniques by which you do this, and the literature, and these are like traditional techniques used in the literature, heavily used by people who do this type of research, like using singular value decomposition, tensor decomposition, and the like. And the idea, again, the underlying principle with all of these things, like the pruning, the quantization, non-zero type of computations, and so on, and low rank factorization, is what you're doing. You're reducing the number of parameters of your model, and that therefore reducing the computational complexity, and therefore keeping the network alive for the longest period of time, especially if it's running part of it which is really running on edges, and therefore keeping it alive for the longest period of time. So implementation on this, why do we really need to implement these large language models on the edge? So these days we also talk about, like we said, so the edge is less capable. So many of these LLMs get trained in big clouds and so on, and then we move some of these models into edge devices, and then we do the tuning based on the local constraints or of the environment. So here, there are a variety of applications that could use of this, edge applications that could benefit from this need. And of course, that gave rise today to things like miniature LLMs or tiny LLMs. So this means like they're not really the full model, but they're a small part of the model which could be sitting on an edge device. And these could be really things like smart assistants, like healthcare. I mentioned examples of this. the last kind of few minutes. You're talking about customer service, for example. Some of these chatbots can be used, and virtual assistants can be used basically to handle customer services. Like I said, the healthcare business is a big beneficiary of these type of applications. And of course, smart assistants, whether they are in homes and cars and in different type of environments, they all basically dependent on machine learning and learning, and they are basically a version of an LLM of some sort, whether it's a tiny version or a full version. Model pruning. Let me see. Okay, I think we spoke about this through federated learning, and so on. Okay, there is one thing here, and that's a growth area actually. Apart from the theoretical techniques, but we're talking about things like edge-specific hardware that's being developed, right? As we need more of this type of environments for the edge, we'll start seeing things like specific accelerators, like we said, TPUs in the past. But we also have things like NPUs, neural processing units, designed specifically to execute models for edge devices. So this is a huge growth area, and that will allow us again to do more on the edge, with these type of very powerful processors. Real-world applications are many, like autonomous vehicles, industrial IoT, personalized user experiences, and so on. And we spoke about this, 2 slides ago, like the assistants, the personal assistants, and the health applications, and the industrial IoT type of environments. I'll just touch, briefly on what you would do normally with a case study like this, and that would basically conclude, this presentation. Say take, for example, the case of using generative AI on the edge. Here, the case of, using federated learning, say for an industrial image classification to enhance detection, say for prediction of equipment failures, right, and defects. This could be something's called preventative maintenance that we normally use, and so on. So you have a scenario in which you're trying to detect, the defects. This could be like, it could be, trying to do this from a drone flying over a field, or it could be like industrial cameras, sensors in the manufacturing facility, or in a mining type of environment. Things like that, right? This is an application in which really kind of we worked on a few years ago, in which we're flying a drone over a field of solar panels. And the idea is, can we really have enough power or enough capability to trying to detect damages? So which PV board, photovoltaic, board is damaged, so we can send someone there to go to go and change it. That becomes a challenge when you have kilometers of this, right? It's in a big field. You could have, hundreds, thousands of these type of, PV boards, and then you're trying to really find which is being defective and so on to really send someone to do the maintenance. So here, that's just one simple example of a case of preventative maintenance. Now, there are issues in this case, right? So in this case, this could be, you could have multiple drones running on top of, separate facilities or multiple facilities. So here in this case, again, you're trying to really select, so client selection becomes a very important thing, again, to participate in this model training. So which clients I need to select in this case to do that? How do we really ensure that the Gen AI models benefit from this new data coming into the system, which is being picked up by the cameras on these drones and so on? And of course, you need to develop algorithms that dynamically kind of jump between or use data generated by multiple agents or by multiple models sitting on multiple drones, for example. Okay. To maximize the efficiency of the training. How do you do that? How do you dynamically select these clients, right? That needs to happen in real time and so on. So that's a challenge in a case study like this. Secure aggregation. You take the data again. If you don't want the data to be seen by everyone, then every client will have its own data, like we spoke earlier on about federated learning. And then the compute happens, part of the model gets developed, parameters get sent back to a local server. And that local server could be something like this, could be like a station sitting on the ground. It does not have to be kind of a cloud environment. Could be just like, one big environment sitting on the ground. And in this case, again, you could use, again, encrypted model updates, homographic type of homomorphic, encryption. Also, you can do things like, secure multi-party computation. Again, you can use SMPC protocols to ensure, again, model updates are combined without revealing individual contributions and so on. And there's the whole, kind of, field on this and trying to really move data between different type of, kind of modules without having to really kind of compromise your identity. The area of medicine is big on this, like this whole, what's known as P4 medicine. When you're like, doing, personalization of medicine or care. And that you see, like we gave the example, a few minutes ago when I said there's a hospital and there are multiple patients, and these are holders of these edge devices. And we need to make sure that, we update their devices all the time. We need to make sure that we are using relevant data to send decisions to each and every device, which is held by a patient and so on. So you can see it's a big field, and it's a very big beneficiary of edge AI or edge intelligence. Finally, again, these are some future directions. Again, like we said, there are the theoretical side of things where we're building better pruning techniques, better quantization techniques. And then there is the hardware innovations, like I spoke about 2 slides ago, with new TPUs, with new NPUs that are being, kind of built and deployed and so on, to allow us to really build, kind of, more sophisticated, or do more sophisticated computation on edge devices. I think improving privacy and security is a bigger issue. We spoke about this, or we touched upon it, not only within the context of federated learning, but within the whole area of edge computing. So because, again, data is being spread across, type of multiple users or endpoints, in which you need to really kind of improve or ensure security and privacy. And of course, coming up with the new scalable edge AI frameworks. That's a huge, big area of research today, to really kind of build and tailor systems, machine learning systems or environments for these type of edge environments, and make it scalable, because we do need to scale these systems, especially when you have edge environments with tens of or hundreds of devices. I think, I can stop here with concluding that, edge computing, again, you can see that it brings us closer to where data sources are, or where data is being consumed. Gen AI can be used, again, with our LLMs or other techniques to, again, creating new content, improving applications across various domains. Again, I'm giving in the blue, some of our recent papers in this field, so you can basically, kind of refer to them. And of course, the implementation of these LLMs on edge devices remains, a challenge, again, because of the computational limitations of these devices, with energy constraints and privacy issues. And finally, model efficiency remains an issue. Hardware innovations are there. And then, of course, privacy, security. And again, Gen AI will definitely be here for a while. And then the combination, or this marriage of Gen AI and edge computing, is creating really very kind of interesting environments, interesting solutions that are, we're getting, fast and smart responses. And of course, doing that in a secure manner. And of course, the application domains vary, and there are many, like you're going all the way from energy to health to manufacturing to maintenance to transport and many more. So it's a very interesting time, and definitely there is a lot of room here for a lot of research and open problems. I'll stop here. Thank you very much, and sorry for the extra time that I took.
Thanks a lot, Albert. Very nice overview, and it was very easy to follow. And I hope the participants benefited from this overview presentation. And please ask your questions in the Q&A section box. So please ask your questions there. In the meantime, I can ask a couple questions to Albert. One is, you mentioned about kind of small language models, like compared to large language models because of the, for example, latency times and also being in the cloud and very large data to access. So kind of like tailoring them, right? Like you mentioned about smaller, tiny.
Exactly.
Now the question is, you will just take the LLMs and then just get the ones that you need for your specific use cases, or you need to design and develop your own tiny or small language models.
So now they're building LLMs tailored specifically, so build in mind with edge devices, right? But also I think you can take part of the model, the big model, take part of it, put it on an edge device. So multiple parts of that model could be sitting on different devices. And that will allow you to deal with the local context, right? For example, say you're having LLM that deals with coming up with the name of the best beaches in the world, right? So I'm happy to be sitting in Sydney and I'm using my mobile device to do this, trying to find the best beach in Sydney to do this, X or Y, or doesn't have rocks or doesn't have certain type of fish that I'm allergic to and so on. So part of that model would be sitting locally, and then that would be dealing with my issues because I'm sitting in Sydney, right? And then of course later when that is done, it sends the parameters back to the main model, which looks at all the beaches around the world and so on. Because I really don't need all that information. So it could be part of the model, or it could be an LLM or a tiny LLM that's tailored specifically to use for edge devices to deal with specific, for example, say pain management for a specific disease, for example, right? Here you don't really need a big LLM, so it could be multiple LLMs that are part of something which is also not too big, and that can be downloaded on multiple devices. So it's both things can work.
Yeah, it's like, you know, when you look at the 80s and 90s, database systems were very hot topics, right? Hierarchical database systems and distributed database systems. In fact, many young people can look into those literatures and learn from there because at the end of the day, these LLMs are also huge databases.
Absolutely.
And
Absolutely.
so you can learn from the past and also use them here. And in fact, what you were saying is also like distributed hierarchical databases, but with, of course, with a lot of twists, right? Because we have a lot of AI and machine learning techniques. And there was also a debate about will LLMs ever reach the human intelligence? Maybe you heard about it.
Absolutely,
So,
yeah.
what is your opinion about that? So since we are
I think
talking,
as we become better at tailoring these things and designing them, I think we'll probably get there. But again, human intelligence never ceases to surprise me, right? So I think it will be a while before we get that. Of course, there are attempts in which you're saying, again, like you remember the Turing test, right? So if ever a machine kind of succeeds in the Turing test, therefore it reached that level of a human being and so on. So we're seeing some attempts, we're seeing some cases in which that is happening. But again, I think talking about something which is so generic and so all-knowing, I think that's yet to be seen. I mean, definitely there is a lot of need for a lot of research and capabilities. Like again, you need even more powerful hardware and the like. So, but I think within the context of services, there is a lot of room there, right? For this type of you get to that level of sophistication in which you would think, say for example, you're talking to a real doctor, right, and so on. That is a possible, right? Because then here you're domain specific, and even within the domain, maybe you can be even condition specific. Like you could be dealing only with X-rays or dealing with maybe the blood samples or whatever, and doing detections and so on. Here you can get to that level of proficiency and accuracy to do that. I mean, we've been working on it with a number of health professionals, looking at different case studies and so on. And in some cases, of course, the system here, we're using it as a recommender system, right? We're not using it as a system that makes the decision. At the end of the day, that the medical practitioner needs to make that decision. But we're finding that in many cases, the decisions are basically, similar. Literally, the system's making a decision, and then the doctor is looking at it and saying, yeah, I would make the same decision. Literally. So we're getting to that stage at least, but like I said, within some application domains, within some services and so on. But hopefully from your questions, I know you meant the bigger picture and so on. That I think that's yet to be seen. That's
You
for sure.
know, I have to mention that there are always these scary comments about, like, you know, in the past it was about Wi-Fi's, and now also about 5G, like the birds are dying and the cell phones create brain tumors. And now there is this huge fear wherever I give talks about these AI-based issues. They are like saying, "Oh, AI will replace the people. AI will replace the engineers, and whatever." I mean, we really should somehow explain that to the people, that stop creating fear for people. You know, in other
Absolutely.
words, what we
Absolutely.
do here is all for the improvement of lives,
Indeed.
improvement of you know, we will give more time to the people to enjoy the life instead of working
Absolutely.
like you know, 100 hours or something. So
Absolutely. And
these will
create new
help.
opportunities, right? So
Yeah,
so you're taking away certain opportunities, but you're
exactly,
creating other opportunities. I mean, we've seen this
exactly,
with every technology, like you mentioned, Wi-Fi,
exactly,
and now 5G and 6G. And
exactly.
so, and you can do the same thing with TVs and radios. And
Yes,
we've seen this throughout human history, in which a new technology comes up, and then suddenly, like, in some cultures or in some places, or even people in general will say, "Oh, no, 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 this is bad, or this is going to put people
yeah,
out of jobs." But again, it depends on how you use it, because you can use AI to do really bad things, or you can use AI to do really good things, right?
true,
We're just talking about health. We're just talking about, for example, manufacturing. We're talking about kind of really normal applications in which you really need better decision making capability and the like.
absolutely, yeah,
But this is true for any technology. Like, you can use
true,
5G to do really bad things, right?
yeah,
You
yeah,
can use, and this always happened throughout human history, especially the last 50 or 60 years, because we've seen advances happen over the last 50 or 60 years so fast that probably surpasses all the advances happened throughout human history. And that discussion happens every few years, right? I mean,
yeah,
even like, you remember the internet. Many years ago they were talking, "Oh, this is going to be bad for people, this and that," and now everybody is so dependent on the internet to go about their daily lives.
yeah,
So it
true,
really depends how do we use technology.
yeah,
But of course, there is a whole field of ethical AI, right, which deals with these
yeah,
issues, and some interesting stuff happens there as well, in which, like, you're trying to bring, you're trying to use AI to bridge the digital divide, right? You're trying to bring more digital capabilities to the people who are, like, disfranchised, right?
yeah,
So you're trying, so maybe that could be also a plus, in which, again, that side of AI, people look into it and look at equal opportunity AI, or, like, ethical AI, explainable AI, that can be used to improve the lives of people. And that one side that we don't see, you know in the public spaces, you don't see a lot of discussion about this, right? But you talk about the other side, which is really AI is going to take your job, AI is going to run the world, AI is going to do this, AI is going to do that.
yeah.
This is yet to
Actually,
be seen.
ITU, International Telecommunication Union, our place is very heavily involved in these AI issues. There are also regulation issues, policies, as you
Mhm.
said, ethics issues, and security issues. So it is a huge area. So the people should not be afraid or scared that AI will destroy our lives and kill the jobs, etc. So
It
anyhow,
will create, I think it will create many new opportunities.
absolutely, that's
And it
true.
will make many of the menial jobs. For example, like, we do work currently on some projects. Some of these could be in the area of, like, agriculture, right? So it
Right.
takes some of these menial hard jobs, and make them a little bit simpler and
Right.
easier when it comes to decision making, right? I mean, I just gave the short example of looking at a field of solar panels, right? I mean, if you normally send workers on that field, they'll be walking for kilometers trying to find
Yeah.
where is the panel. So, of course, there are other techniques you can use to really detect which panel is faulty and so on. But you can do that with a very simple solution. You send a drone collecting photos and deciding
Right.
which, and in this case, we reached accuracies of 98%, right? So we're able to
Absolutely.
detect
Yeah.
these faults. So why would you want a human being to go and do that? So trying to make
So
life easier, right?
absolutely. So the quality of life will be improved through these
Absolutely.
technologies. Actually, that's the
Abs-
objective, not losing the jobs, So
Absolutely. Absolutely.
they will not be jobless or something. So there's a question actually, Muhsin Iftikhar, he never follows the rules. So last time he wanted to talk, now he wrote this here in the webinar chat instead of Q&A box.
Yeah,
He
I
says,
know Mohsen
your
from many years ago.
student, your his advisor, PhD advisor. So he has the question about, is there any possibility in the future that LLM can help to devise real-time scheduling for augmented and virtual reality applications at the edge?
Of course, I mean,
Yeah.
virtual or mixed realities are one beneficiary again of this technology, like the edge, because these could be all edge devices. You could be holding multiple, meeting in which, a hologram of you appears in that meeting or whatever, but you're sitting at home, maybe for like, for Ian sitting in Istanbul, me sitting in Sydney, someone else sitting elsewhere. But all of that is done through VR hardware and so on. And VR hardware, especially if it's kind of distributed across multiple geographic locations, can be considered as edge. And of course, the AI or the machine learning will manage that to enable this type of really kind of real meeting feeling, right? So there is definitely that. I mean, VR is beneficiary already. Actually, many conferences these days, like whether they're image processing, vision, VR, distributed systems, networking, etc., they have sessions and sessions on machine learning, and its uses, right? So definitely, yeah, there is a lot of room there. I mean, it's definitely it's definitely not something that you would even have to question. It will happen.
He has similar questions. So I don't need to read this. So he's asking similar question. And so I want to have, I don't know, we don't have, here's one. Q&A. No, there is no. Ammar Mutana is asking, can we use light version of neural network due to edge devices, limited processing power and storage capacity?
Right. I mean, this was the whole idea of this, right? I mean, like I spoke, briefly about it. And that's the idea. Why do we use pruning, quantization, trying to benefit from the fact that you have a lot of zeros in the network? Think of a neural network that you could represent the weights as a matrix, and this matrix have many zeros. So why do you really need to involve the zeros in the computation? Just involve the real numbers. So you store them in a certain way. You do the computation in a certain way, so to reduce the computation load. So there is, and that's the whole idea of running smaller, ML models or lighter ML models on these edge devices. So yes, definitely.
There is another question, a secret attendee, anonymous.
Right.
People love to be anonymous. I don't know why.
That's fine. That's fine.
They are scared of something. When
can you read it, Ian? Yeah, I can.
Yeah, I'm reading. When can we expect that deployment of edge-based AI begins?
It's already happening. It's already happening. It's already happening. So it began already. So it's happening. It's being deployed in a variety of environments. Again, they're very much like, like I said, when Ian asked, I said they are service oriented. They could be like, application specific. They're already being used. I mean, we use it with a variety of collaborators in manufacturing environments and health environments, agriculture and the like and so on. So they are already being deployed. And I think if you go and pick up the proceedings of any conference in the field, you will find that, there are like, many case studies, many papers will be talking about deployments and so on, whether they are in transport systems, whether they are like, in personal assistance or in health and the like, So they're already here. Okay.
Oh, by the way, anonymous attendee is my colleague at University of Iceland, Sami. He's surprised that he says, why is he shown as anonymous? Thank you, Sami. I'm really sorry. So he's in Iceland, in Reykjavik. So there's another one. I don't know, is it the same, Sami? Anonymous attendee, he says, from the perspective of serving edge cloud in the telecommunications domain, does federated learning present an opportunity to enhance the efficiency of network orchestration from end to end?
Right. So, federated learning has been around for a long time, right? So many people, when you talk to them, they say it's already passé. We've done so much with federated learning, and we need now to think of something else, right? But again, if you have some basic applications, then FL will do the job. And we know we have so many techniques out there that or at least alterations of it. I mean, I myself with my collaborators, we've generated more than 20 papers on variations of federated learning, right? And I'm sure you'll find hundreds of these in the literature since it came out a few years ago. So yes, it's usable, but I think also now we need to think of other techniques that also deal with the limitations of federated learning as well, right? It cannot be seen as the solution for every problem. It's useful, it can be used, and we're using it effectively, and there are variations or different versions of it to deal with federating computation, federating storage, federating bandwidth. So there are versions of it. But of course, there is definitely, as we see more advanced hardware coming out for the edge, we see more lightweight type of algorithms being developed for the edge, ML algorithms. Now there'll be definitely room for newer techniques, for new innovations. And so yes, you can do that, but we also probably need even more sophisticated type of new innovations as well.
Let me ask you one more question, and I will
Sure.
let you go to Alessia for life lessons session.
Sure.
So, as you know, to my knowledge, all the existing LLMs are all English-based, right?
Right.
Now, when you go to South America, there are some countries they don't care about English, unfortunately, so like really. And
Absolutely.
or some Arabic countries, so although they learn English, but still, like Northern Africa is still heavily French and all that. So anyhow, I asked some people, do you have LLMs in your language? The question is, oh, we don't know this and that, or they use Google Translate. And as you know, Google Translate is not always accurate, right? So first of all, the information which comes from LLMs may not be accurate. Then you translate, it's double not accurate.
That's
So do you know what is the status that are there other countries? I know TII has Falcon, like I work for Technology Innovation Institute, but it's in English, Falcon 2. So I'm not sure that there is an Arabic version of it or some other, languages or Espanol or Spanish. So what is the status of that? Do you have any?
I think these are evolving. Definitely, even the big players are definitely building these because they see that there is a value for this, right?
Yes.
So I think these are they're gonna happen if they're not already happening, and that is where even if you have an English-based LLM, when you have these smaller LLMs, if you will, miniature, separated geographically and so on. Here you can also do the local context, right? Whether it's the language, the nuances of the different languages, how do they really translate this or translate that? I think that there is a lot of work here, but that's a very complex problem to solve. Very complex. But I'm sure there are attempts for sure.
I can imagine.
To do this. Because it's a big service, right? It's a big service.
Yeah. Thanks a lot, Albert. Very nice. And I
you.
enjoyed it, and I'm sure the participants also enjoyed it, as well as the future followers of our webinars will enjoy this talk. It was very informative. Thanks a lot again.
Thank you very much.
And Alessia, you take over, and please go ahead and ask your questions.
Thank you.
Thanks
Thank
again,
you,
and
thank
thanks
you very
again.
much.
Thank
you. Thank you, Professor Zamaya, for your very comprehensive talk. It was extremely clear, extremely interesting. Thank you. So now it's time to move to the Wisdom Corner, live life lessons, which aims at offering a special angle to this series of webinars, adding a personal touch. So if you agree, I would start with my first question to you.
Sure.
So which is your hard-earned life lessons or even failure that you would like to share with us today that might perhaps help someone attending the webinar?
I think, in a life in which I'm sure, others probably in the field, I mean, even other people in this business know that, you never, you will have a lot of successes, but probably even more failures. For every success, you would have maybe 10 failures. So when that happens, you don't stop, right? I mean, you need to become better at picking up yourself, picking up the pieces, and just moving forward. I mean, we do have a lot of disappointments again, professional disappointments I'm talking about here, but that also reflects in your personal life as well. I mean, which might not be perfect, and for many of us. So you learn basically to become better and better at accepting, failures, right? And then being able to take the lessons that you learned, and then hopefully, you lower the number of these failures that happen. It's just a matter of you becoming more resilient. And I think probably in this business, at least in technology in general, I think, I've been involved with not only this research, but also in the past with startups, and currently also looking at some opportunities in that sphere. You learn again that, okay, if something failed, what did you learn? Can we really take this and then, for the next opportunity, and make sure it doesn't happen again? So I think, one of the things is just like, you become better at being resilient, right? If there is anything, right? And resilience is important, not only for profession and technology, but it's also important for our own personal, existence, right? We have a lot of disappointments, in life and so on. And if you're not resilient, then you just give up and you stop, right? And that's not an option.
Yeah, wonderful. Resilience, definitely. We take note of that. In which field and which topics would you recommend students to study? Is there any current trends or emerging areas of research that you find particularly exciting or promising nowadays?
Right. So I come from myself from the distributed computing community. Over the years, I've done also work in mobile and networking, like Ian mentioned. But also, like these days, we see that machine learning is everywhere, right? So I think this is definitely a big field, and it will touch many areas, because in the past, machine learning or AI used to be confined to the specialists or the people who are doing research in these fields. But today, when you go to the big events in machine learning and AI, you'll find people coming from different disciplines, from databases, from distributed systems, from networking, from medicine and so on, even mathematics and the like, and they're all contributing to this in their own ways. So I think, this will be with us for a while. I mean, and then with the emergence of technologies in various fields, for example, in communications, you have, you're having better hardware evolving. We're talking about 5G and 6G, which is going to make things even better. The same thing, you talk about that in distributed systems. As we get better hardware and better systems and so on to run these algorithms, we're going to have more opportunities again for the use of and applications that use these type of algorithms, machine learning, that is. And of course, you take applications, right? I mean, from medicine to manufacturing to, transport to health and so on. You'll find there is a lot of need for this type of decision-making type of capabilities that will allow different people to have equal opportunities, right? So in this case, I think machine learning within the context of this technology probably is going to become more like, an equalizer, right, of opportunity. Hopefully, it becomes an equalizer of opportunities, because it's gonna make the use of certain complex capabilities, available to the common person, right? Not to the specialist or to someone with a higher degree, or someone who has a machine learning or AI specialist. So I think really it's going to be really kind of a field that's going to cut across so many fields. And I think really I always found that the intersection of multiple fields, sometimes when they happen, working at the intersection of fields is really where all the great ideas gets created, and interesting ideas get created.
Wonderful. I like the idea of equalizer. That's a very nice concept and very good. We should pursue that.
Absolutely.
What advice would you give to young people interested in pursuing a career in academia or research? So which key skills, apart from resilience and qualities, you believe are essential for success in academia and research in general?
I think see, because again, different people come to do research and come to academia. You don't have to be really, not everyone is a genius, right? So some of us are hard workers, and we compensate for the lack of mental capability, if you will, with hard work, right? So I think with hard work comes really discipline. So if you don't have discipline, it's going to be very hard to really, if you cannot be disciplined and being able to work sometimes even when you don't feel like working, or trying to finish something, there's a deadline and so on. That that becomes a problem. So discipline becomes the number one thing. Of course, you have to have passion and you have to be passionate about what you're doing. That's crucial. But sometimes we go through ups and downs and we feel tired, we feel exhausted, we feel like, deflated. So having the discipline always brings us back to, you need to focus on the mission, you need to focus on the end goal and so on. So discipline becomes more important than even, because with discipline comes hard work, right? And that becomes more important than just being smart.
Yeah, very clear. Resilience, passion, hard work, and discipline, definitely. The good recipes for success. And what initially sparked your interest in your field of study, and how did you pursue it? I mean, really at the beginning of your career.
Right. So in my case, when I got my PhD many years ago, actually my PhD focused on robotics, right? So at the time, robotics was, it still is actually, but it was a basic field starting, with research in a variety of places, but again, very basic because I'm talking here about the late 1980s. And then the idea was like, can we really build better systems and so on? So I got into this from looking at it from a real-time system type of angle, and then looking at to control these robot arms and so on. And for me, this was really exciting because it's something that you've never been exposed to in your undergraduate life, and it was more like an advanced topic that some people said it has promise, some people said no, it's going to disappear after a while. So it was more of a challenge, right? And finding something that I would feel excited about for the longest period of time. And that happened. I mean, I worked for a long time on robotics, and then using these, real-time systems or distributed systems, trying to really manage these robotics environment. And then, of course, that led to other things, as you get, kind of more, you get like, more mature with your career and career decisions and so on, and looking at other application domains and the like. But definitely that was the key, was like to look something that you could be excited about. It's unknown, you don't know, you feel like, hey, this has promise. And then of course during that time I had the benefit of talking to many mentors, right? That you spoke to them. These were your professors at university, and you take their opinion, right? I mean, you listen to them, you try to take lessons from their own reflections on their own journeys, and then hopefully you can use that to really kind of make an impact on your own. And I do the same thing with students these days, right? I mean, you talk to them, you try at least to share some of your because I think that's an important part of what we do. Our role is to also share some of these experiences and so on. So like I had mentors in the past, and I try to be a reasonable mentor, not perfect, but hopefully reasonable. But definitely the mentors, the discussion with these mentors was important. And that's what I say to people who come say, like, I want to do, I'm not sure whether I want to do a PhD or not, right? Or want to become an academic or not. And I say, look, if you're ambivalent, you're not sure what you want to do, you talk to as many people as possible that you would think that people that you come across, that you respect their opinions, you might see their journeys as being successful journeys. Talk to them, and then take from that, like you can take from that whatever information is going to be useful for your own decision. And you could use it sometimes to say, look, I don't want to do a PhD immediately or go into academia immediately. I want to try my luck with going into industry and doing some stuff out in the real world, so to speak, right? So, and then you do that, and so that at least when you come back to do a PhD or come back to becoming an academic, hopefully you don't worry too much about, oh, did I miss out on anything in the real world, right? And of course, much of the stuff we do also has an impact on real world applications, like just we spoke in this talk. So it's really this decision making that needs a lot of talking to mentors, doing a lot of self-reflection, seeing what you want, what you like, and because you bring part of your personality into this, right? So I mean, if like we said, there are things like discipline, resilience. This comes with time, because you develop. It's a skill that you need to develop with time, and you get better at it. But initially, it has to be something that captures your imagination. You could feel that you could be passionate about, for a period of time, so you don't give up on it. And sometimes when you're not sure, then I always say go out to industry, try your hands at work for a company and so on, and work for 2 or 3 years, and then there is always time. You can come back and start this new journey, right? So it's always like that. But again, like I said, it's reflection and talking to people who've gone through the journey themselves.
Wonderful. So talking to people, talking to mentors, and you said to also have an impact and on your own. And this brings me to my last question to you. Could you tell us one of the most tangible contributions that you have made in your career that had an impact on your life, professional, but also personal, and on others' life that you're most proud of?
I think, some of the stuff we've been doing in the last few years in the area of biomedical. So again, with using edge, with using machine learning and so on. And some of these we're starting to see that were used in real life setups, right? And it's very rewarding to see that something that's gone out of the lab, gone out to the real world, and people are using it, and it's making an impact on the lives of others, improving the lives of others, and so on. And as we go through a career, I think some of our priorities also shift with time. So, you do research, you're passionate about what you do, but at the same time, you start wanting to see, what you're doing can also be good for social good, right? So that's also an important part, which I think it's very gratifying to see some of that stuff we're doing is being used and useful for real world type of applications and being used, by patients and the like and so on. And I think that's very gratifying, very important.
Wonderful. Thank you so much. I really enjoyed this Wisdom Corner. I hope you did too.
Thank you.
I
Thanks a
ask
lot.
Ian to come back with us for our closing.
Yeah, I'm back here. Again, thanks a lot, Albert. It was
Thank you.
excellent, really. We appreciate it. It must be at midnight now in Sydney, right?
It's close to
A bit
midnight.
late.
Well, thank you. Thank you.
Thank you so much for being
Yes.
with
Thanks.
us and
Thanks for the kind
sharing.
invitation. I've enjoyed meeting you again, Ian. Good to see you again.
Same
And
here.
thanks
Thank
for the kind invite. And I look forward to hopefully, seeing you in a much in a different time, in a different geography, maybe Istanbul, because it's
Yes,
the
I
city
hope
that
so. Yes. Yes. Thank you, Albert.
we hopefully
Thank you.
meet there and celebrate. Thank you very much again.
Thank you so
Yes.
much. Thank you. And so
Our
now,
webinar will
Ian,
continue. Alessia, you want to
Yeah,
mention that next
exactly.
week?
We'll see our participants again live next week at 4 p.m. Geneva time for a webinar with Professor Raouf Boutaba from the University of Waterloo, Canada.
Thank you.
Thank you so much, everybody. Thank you.
I wish you
Bye-bye.
all
Thank you,
the best.
Professor Zumaya.
Bye-bye. Bye-bye.
Thank you.
Bye-bye.
Thank you.
Thank you.
Bye-bye.
Ciao.
Take
Bye-bye.
care. Bye-bye.